Okay, lesson 32, X-rays and the Compton effect. Okay, so you guys have heard of X-rays, I'm sure, before. You've probably gone for an X-ray or something before, or know somebody that did. At this time, they didn't know what X-rays were, right? They were undiscovered at this point. So a few scientists actually almost discovered them doing these different cathode ray tube experiments. But it wasn't until Wilhelm Röntgen, I don't know. Anyway, he discovered X-rays, and the reason that they're actually called X-rays, and they do this for a few things, is it was unknown, right? So like often they'll say X in place of unknown. It's kind of like Planet X, right? It's like the unknown planet, or X-ray, the unknown ray. So that's why they're called X-rays. Still, they just kind of kept that name. And what he discovered was that it passes right through a lot of substances, or a lot of things, and it gets reflected by others. So, you know, that's why we use that, right? That's why we take X-rays, is because it passes, these light rays pass right through your skin, right through them, like any kind of meat or fats or anything like that, but they bounce off of bones. So we actually get a good picture of that, right? Where if you're looking at your hand, you can get these X-rays that will travel straight through, but then some of them will hit the bone and then bounce back to a device where we can see that, right? Like we can't literally see X-rays, but we have machines that can see X-rays, and then and then they turn that back into visible light spectrum that we can see, right? So big discovery, right? It was put to use immediately. The way that they were discovered was with our cathode ray tubes, right? So we've done a bunch with cathode ray tubes now, right? So if you had like a cathode here and an anode here, then if we can end up shooting electrons from this plate, and then if they smash into the end of the plate at the backside there, it'll emit X-rays. And it comes really from decelerating electrons. So you get these electrons that are slowing down really, really fast, right? So you get an accelerating charge, and so really you end up getting light, right? It's just a really high frequency, or a small wavelength electromagnetic radiation, right? Okay, but anyway, I digress. So at the time, though, they didn't really know what it was, right? So is it a particle? Is it electromagnetic radiation, right? They didn't know this at the time. They just knew that there's this weird thing that passes through, you know, some things and not through other. So what the idea was that they're like, well, what we could do is if this thing can travel through these slits, right? So if we go way back to our light unit, then you remember how when we send light or photons through these double slits, how that ended up making an interference pattern on the backside, right? And that was the telltale sign that light is a wave, right? Because when it comes through here, it creates it diffracts around and then interferes with itself, right? So we end up getting these interference patterns on the screen on the backside, right? Well, they said, well, okay, let's try that with these X-rays to see, is it in fact a wave like light? The problem is that X-rays have a very, very tiny wavelength, right? And a really, really high frequency. So the slit opening that you would need to do this double slit experiment to see would be very, very small. It would actually have to be like 0.1 nanometer diffraction gratings to actually see any sort of diffraction patterns if they were going to happen. But they theorized, or they thought at the time, that actually crystals were thought to have about that spacing between them. So they were able to use crystals, so shine it through a crystal, these X-rays. And in fact, that when they did that, they ended up getting that interference pattern on the back on the screen on the other side. Okay, so turns out X-rays really are just a member of electromagnetic spectrum. All right, and we've been talking about that for a while, so that shouldn't be new to you guys, but it was new to scientists at the time. All right, so It turns out the best way to make X-rays, or for them at the time anyway, was to set up a cathode ray experiment. So like this, cathode ray apparatus, I should say, and shoot electrons from your anode there, and have them crash into a tungsten metal plate, and then put it on an angle. And the reason for that, the reason for using tungsten is because tungsten has an extremely high melting point, and very, very hard. So what you could do is you can end up transferring all of this energy from these electrons being shot out, would smash into this tungsten, and then what would happen there is those electrons are slowing down very, very fast, which means they're accelerating. They have a really, really high acceleration, right? And if you get a really, really high acceleration on a charged particle, right, then you get light, right? We talked about that a few times, that if you get an accelerating electron, then that's what starts that electromagnetic radiation on its journey. Same thing if it's slowing down though, right? We talk usually in the context of like an electron accelerating downward, but you get the same phenomenon. If you've got an electron and then it slows down really fast, right? That's also acceleration. So that's going to send an electromagnetic wave. So really, really high acceleration or deceleration. And then you end up getting that really, really high energy photon, which is an X-ray. Okay. So that's the idea there. So now, what he was able to do was say, well, okay, well, if we've got really this experiment here, and we've got these electrons, right? So let's just say there's like one electron shooting into this thing, then that electron has energy, right? It's got kinetic energy, whatever it has, you've given it a lot of speed, so it has energy. And then when it smashes into that thing, if we assume that all of the energy of the electron gets converted into the energy of the outgoing photon, then we can set up a simple experiment or a simple equation from that, where we can say the energy of the electron, like before, is equal to the energy of the photon after. Okay, so just one for one. One electron gives one photon. Okay, and the maximum amount of energy that it can have would be, like I said, if all of the energy was converted. So there we go. So we say the energy of well, in this case, it says energy of the photon. Well, that would be because you're converting all of the energy of the electron into the photon, right? So, okay, so, oh no, so, actually that's not photon, that's I'm saying electron, or the electric potential energy, sorry, is what P stands for, not photon. Okay, so in the end there, we can say, okay, well, the energy there is going to be Q times V. So remember, that's the charge of an electron. So 1.6 times 10 to the negative 16. No, 1.6 times 10 to the negative 11. Why did I forget that? 1.6 times 10 to the negative 19. Sorry. Okay, anyway. Times whatever the voltage was. And then our outgoing energy is just Planck's constant times the frequency. Or we can rewrite this as, instead of with frequency, you can write it with wavelength, where it's just the speed of light over the wavelength. Okay? So that's the idea. We'll do an example below here. This is a good one to look at too. This is like a little bit tougher than what I'm going to do in a minute here. So this would be a good example to look through. Okay, so in general though, so here's our properties of these new X-rays. So is it a wave? Is it a particle? And this is the big question. This is what we're going to get into the next lesson there too, is things get really weird as you get smaller and smaller, right? And that is this quantum mechanics idea. So, and it turns out that X-rays with these tiny, like really, really small waves, they kind of take on a bit more of a particle property. Okay, so they are waves, right? They were able to show that with the diffraction pattern to say, okay, well, these things are waves. They belong to the electromagnetic spectrum, but they also kind of act like particles, right? So it's called this wave-particle duality that we're going to get into. And this is kind of like, you know, one of the first parts of it, where these photons are waves, but then they also kind of behave like these wave packets that I was talking about before, right? So they're like these bundles of particles that are being shot, right? So anyway, the wave characteristics of X-rays would be that the X-rays can penetrate opaque objects such as wood, paper, aluminum, human flesh, but they don't penetrate bone. And X-rays can be diffracted by crystals. So the reason why those are wave properties is because, let's say if you've got, you know, this is my skin and these are like the particles in my skin, right? Well, because it's a wave, like if it was a particle, then quite often what would happen is that the particle would bump into those particles in my skin and they'd bounce that way, right? And they'd kind of bounce around. But since it's a wave nature, what can happen is that the waves kind of just go like up and around and like avoid the particles in my skin, right? And that's kind of a wavy type of a thing. And then the fact that X-rays can be diffracted in crystals, that's what I explained above, right? Is that you get that diffraction pattern on the screen on the other side, like we did a whole unit on, right? And that is very wave, like that's definitely a wave, right? Once you see those diffraction patterns, that's a wave. Okay, so they know it's a wave, but then it also behaves like a particle, or what we've been calling a photon, because X-rays will ionize gas. They collide with electrons and drive them off molecules to produce ions, they're called. But anyway, so what that means is that you've got a lot of things like bumping into other things. Like if you've got this X-ray, will end up hitting an electron and bumping it up out of its orbit, right? So yeah, that's more of a particle type thing. X-rays will cause electron emission in water, which is really for the same reason as above. And then X-rays will affect photographic plates. And that photographic plate part, why that's particle-y, is because photographic plate would be as if you had these electrons stuck to a plate, and then you bring in, you know, an X-ray, and it's like a 1-for-1, right? You get one photon of light comes in, and it knocks one electron off. So that's particle-y as well. Sorry, these aren't technical terms. Okay, so part two. This lesson's kind of broken into two parts. You've got X-rays, which we did above, and then this is part two, and this is the Compton effect. They're related, but kind of different. So I'll let you guys read through this kind of bio of Compton. Yeah, so you guys can do that. In the end, he ends up spending most of his time, or not most of his time, he's more focused on discovering if photons themselves, like if light, actually has a momentum. Okay, and I'll just let that sink in for a second, why that's weird. So he's saying that he thinks that you get a wave, right? A wave, really like any other wave, but he's looking at X-rays. And he says that wave, if you're standing here, if I shot enough of these things at you, these like X-rays, then if they have a momentum, he's saying, I think they have like a P, like we learned in our first unit. Then if I shot a whole bunch of those at you, I could actually knock you over with light, right? Which is a crazy idea, because it really means if I had like a really, really strong flashlight, then I could actually like knock you over with that flashlight, right? That's how strange this idea is going to become with light itself having a momentum. Okay, so let's kind of follow his logic though. So this is what he thought, or what he, like the math that he was showing to prove it. Because he said, okay, well, we know that momentum is equal to mass times velocity, right? That's lesson 1. That was our first unit. That's what we did, right? Okay, so then he said, but Einstein's famous equation, E is equal to mc squared, we could say, well, okay, well, mass is equal to E divided by the speed of light squared. We haven't really got into that a lot. We will. This is going to be a big equation for us pretty soon. So he said, okay, well, this is the case that mass is equal to energy divided by the speed of light squared. Okay, then if I substitute this in for mass, right? So instead of a mass there, I'm going to substitute that in for E over C squared. Then he said, well, okay, well, if V really is, it's traveling at the speed of light, because it is light, right? We're talking about the momentum of a electromagnetic wave. Then, okay, I can just replace that with a C. So that's what he did there. And then canceled, one of your C's. And he ended up with a very simple equation. P is equal to the energy of the photon divided by the speed of light, right? And he said, okay, well, and we can look at this a little different and say, well, Planck's constant, or Planck's equation, I mean, is this or this, right? Depending on whether you're looking at frequency or wavelength. So you could also write this as momentum is equal to Planck's constant times frequency divided by speed of light, or momentum is equal to Planck's constant divided by the wavelength. So either of those are true. Now, on your, just where to find this, because these are new formulas for you guys. These are on your formula sheet, but I just want to write them the way they're written on your formula sheet because they're a little different. You guys have it, well, you do have this one. So you've got momentum is equal to Planck's constant over wavelength. So now when you guys see this, you should be thinking light, right? Like light waves. Don't confuse this with momentum of a particle or something like that. And then the other way it's written is E is equal to PC. And just notice that that's the same as this equation here, just rearranged a little bit different. But we don't have the frequency one. So it's up to you, if you're given frequency, to say, okay, well, I could replace wavelength with C over F, right? And then rearrange that to get P is equal to Planck's constant times frequency over C. But this one's not on your formula sheet. So if you're given frequency, then you'll either have to change it to wavelength first, or rewrite the equation this way. So either one, just and it's up on the top right. It's under quantum mechanics and nuclear physics now. Okay, so anyway, so he came up with a math. So here's the idea. Like he's like, okay, well, this makes sense according to the math at the time, the theories of the time. But good scientists, you always got to test it. So here's what he did. He originally experimented with X-rays, and he was bombarding different types of atoms, but there really wasn't any effect happening. So he changed it to electrons, because electrons are very, very small, right? So very, very tiny mass would have more of an effect if you smash a photon into an electron. So here's the idea. Like this should look kind of familiar to like unit 1. So he just went, okay, well, if this thing really has momentum, then I should be able to shoot an X-ray into an electron, and it should move the electron. And that's exactly what happened, right? So you end up getting the electron getting shot off at one angle, and you get your photon or your X-ray getting deflected at another angle. This really is momentum from the first unit, but now we're dealing with light as one of our objects. Okay, so this one it's strange again at this small level when we're talking about like an electron, right? Where the collisions that are happening are purely elastic collisions. Okay, well, what does that mean again? So elastic collision means that all of the energy is conserved, which is weird. Like that actually really is weird, because what that means, like before when we had like, object 1 hitting object 2, and that would go that way and the other one would go that way. Remember how with the energy, there always would have been like heat lost. So if we set it up, you'd have like, energy before is equal to energy after. But then you'd have plus, the energy lost due to heat or the, yeah. So yeah, we don't have that anymore. There's no energy actually being lost due to heat, which is very strange because that doesn't happen at our macroscopic level, right? Like at our everyday world that we live in. Any interaction, there's always energy loss due to heat, right? But there's not in this case, which really is strange. But anyway, so what we can do now is set it up really similar to the way we did it in unit 1 with conservation of energy, and say energy before, right? So that's your incoming X-ray, right? That's this one, the energy of this is equal to the electron's kinetic energy, right? So the how fast the electron is moving out, or the energy it has because of its speed. So 1/2 mv squared. and then the energy of the photon leaving, right? So that's going to be hc over the final wavelength, right? So yeah. And then, like I said, typically you'd have, like, really, if you're doing this precisely, you'd have plus the energy lost due to heat or friction, right? But that doesn't happen here. Okay, so that's the conservation of energy, right? So energy is always conserved in these, which is, sorry, so energy is always conserved in these situations, and momentum is always conserved in the Compton effect. Which isn't true for big objects, right? So remember, energy is like never conserved when we were talking about big objects. It was always just momentum that was conserved, right? So now, if we think about this in terms of momentum, we can say the momentum before is equal to the momentum after, is all this is really saying, just like above. Now, it's drawn this way. We did kind of go through this a little bit. When we did our equations, we did them a little bit different, right? But this is just saying the momentum before of the wave before, right? That's that line, is equal to the momentum of the electron plus your photon after, right? So the length of those arrows are the same, right? It's from there to there. So you can set that up with this. That's a non-right triangle. So we could use sine law or cosine law to solve it that way. Or the way that we did it quite often before with momentum is we would say momentum, oh, that was not a straight line. A little better. Momentum of the photon before, call that like initial. So that'd be like my energy or my momentums before. And then you'd have your momentums after. And do you remember how we just like drew these out as separate little triangles? So we could have, I'll make that green. Momentum before, so that'd be like the one of momentum of the electron before. And then you could have your momentum of the photon after, or final. And then we turn those into those little triangles, right? So it would be like that component of it, and maybe our y component. We'll make red. And then do you remember when we set it up, we had to say that the sum of the, it's the sum of the momentums in the x before is equal to the sum of the momentums in the x after. And we also did the sum of the momentums in the y before is equal to the sum of the momentums in the y after. That's what we'd have to do here too, right? You'd have two equations, like the blue arrows and the red arrows. So anyway, you could set it up that way, or using the sine law, cosine law one. So whatever you prefer there. Okay, so being the smart guy that he was, Compton used some of Einstein's equations from his special theory of relativity. We don't really get too much into that in the Physics 30, but this was like a thing at the time that was popular in the science community. So he used some of Einstein's special theory of relativity to come up with this equation. And this equation tells us what the angle scatters at, or sorry, what the angle that the photon scatters at in this experiment. So this one is on your formula sheet, but it's not written with it split up, right? With your final wavelength minus your initial wavelength. So make sure you guys find that one. It's up on Quantum Mechanics, Nuclear Physics too. So we'll do an example of that below, but yeah, the idea really with this equation, I guess, is just that if we had this experiment set up, this equation would tell us what this angle was just by knowing what your final wavelength was and your initial wavelength, right? So that's what's going in here. So your final wavelength and initial wavelength. And then Planck's constant, this will be the mass of an electron because it's an electron that it's hitting. And then your speed of light, and then that's your scattered angle. But yeah, we'll do this in a little bit here. So this discovery ended up getting him the Nobel Prize in physics, because of the significance of a photon being both electromagnetic radiation and a particle, right? Like this was a big idea. because this is very, sorry, this is very particle-y, by the way, right? When you've got something hitting something else and knocking it in a different direction, right? Like this really shows the particle nature of an electromagnetic wave. Okay, practice problems. Okay, so number 1 says a color TV operates using a potential difference of 60 kilovolts. If electrons are completely stopped by the anode, what is the wavelength and momentum of the radiation produced? Okay, so we will set it up again where we'll say, okay, all of the energy of the electron is going to be converted into all of the energy of the photon. And remember what that is. That's just saying you've got these electrons that are being shot at a really high energy. They're being smashed into like a tungsten plate, and then that is emitting a photon, right? So we're saying all of the energy of this guy isn't being converted into all of the energy of that guy, right? That's what we're starting there. And yeah, so then the energy of the electron here, well, it got its energy from being, from having a voltage applied across it, right? It's happening in a cathode ray tube. So we can say that the energy came from QV, right? The charge of the electron times the applied voltage. Okay, and then the energy of the photon. Okay, so it's asking for the wavelength. So I'm going to write this in terms of wavelength. So I'm going to say Planck's constant times the speed of light divided by the wavelength. So then rearranging this, just bringing wavelength up and QV down, we'll say the wavelength is equal to Planck's constant times the speed of light divided by Q times V. Okay, so putting that in, we get wavelength is equal to 6.63 times 10 to the negative 34 joules times seconds times 3 times 10 to the 8 meters per second divided by charge of the electron is 1.6 times 10 to the negative 19 coulombs. Sorry for the messy writing there. Times, okay, and then 60 kilovolts would be 60, and then kilo is 1,000. So just 3 more zeros. Volts. So 4 zeros in total. So then our wavelength is 2.1 times 10 to the negative 11 meters. Okay, and then momentum. This one won't be too tough because we just have a simple equation for this now, right? So the momentum of light, of a photon, is just momentum is equal to Planck's constant divided by wavelength. Okay, so momentum is going to be 6.63 times 10 to the negative 34 joules times seconds divided by our last number there, 2 point. Actually, you know what? I rounded that. So you just make sure you go back to your calculator, get the more accurate number. It really should have been that 2.0719, right? Like using like more digits there, times 10 to the negative 11 meters. Okay, so your momentum ends up being 3.2 times 10 to the negative 23 kilograms times meters per second. Okay, now number two. Number two, I'm actually gonna do a different question. It doesn't turn out that well. I end up getting an error when I have to find your angle there. So what we're gonna do is go down to number 6, and I'll do number 6 with you. So we'll cross this one out. Number 6 has a lot of the same. Or sorry, number 6 on part 2. So there's a Compton effect, and then we're gonna do number 6 on here. So this one says a photon of wavelength 2 times 10 to the negative 11 meters collides with a stationary electron. As a result, the electron moves off with the speed of that. And it says, what's the wavelength and angle of the scattered photon? Okay, so what's going on here? So they're saying that we've got a wavelength. Okay, so we got our photon coming in. You've got your electron that's going to hit. It hits the electron, bounces off at an angle. And then you got your photon being scattered, right? And it's asking for what is the wavelength of the new photon being scattered and what angle was it scattered at? That was theta, by the way. Theta. Okay. All right, so what do we got to do here? Well, we're going to set this up first off for energy. I want to find energy. I want to find the wavelength. So I'm going to set this up in terms of the conservation of energy formula because I can find the wavelength pretty easily from that equation. Okay. So here, so we're going to say the energy of the X-ray is equal to the kinetic energy, or the energy of the electron, whatever you want to do. I'll put Ke for kinetic energy of the electron. We'll put the little dash there for make sure you know it's an electron. Plus energy of the X-ray. And I'm just going to put a little tick on the top. Remember that prime symbol to mean like after, right? So that's just talking about this one. Okay. So the energy of the X-ray before, well, the energy of a wave, we have an equation for that. It's going to be Planck's constant times speed of light over the wavelength. Okay, and we know what the wavelength is, right? It tells us what the incoming wave is. That's going to be equal to, now remember, all the energy that the electron has is all due to its speed. So 1/2 mv squared. And then plus, and then that's again going to be the same as before. So then hc over, and then this will be wavelength. And I'll put a little tick at the top or that prime symbol to mean after, right? And then that's what we're after, right? We're after our second wavelength. So rearranging this guy, well, let's do just piece at a time. We'll do it even with like without putting the numbers in first. You could put the numbers if you like, but I want to get more used to just rearranging the equation and then putting the numbers in. So I'm just going to move this term over there for step one. So we'll say hc over wavelength minus 1/2 mv squared is equal to hc over that wavelength prime. Okay, now this seems like it's going to be really complicated, but it won't be too bad. I'm just going to move this wavelength out of the denominator. I'm going to move it up to the top there, and I'm going to move this whole chunk down to the bottom, right? So I'm just really swapping out those two. So I'll say the wavelength prime, or after, is equal to hc over all that stuff, right? hc over wavelength minus 1/2 mv squared. And then that's probably good. We could actually just put all of our numbers in there, right? So we'd end up having the wavelength after is equal to 6.63 times 10 to the negative 34 joules times seconds. Times 3 times 10 to the 8 meters per second for light over 6.63 again. 6.63 times 10 to the negative 34. And here on the bottom, I'm going to put that all in square brackets, kind of keep it separate there. Times 3 times 10 to the 8 meters per second over, and then this is our original wavelength, right? So that's going to be our 2.00. So I'll just say 2 times 10 to the negative 11 meters. Okay. And then minus 1/2 times, and then this will be the mass of the electron. So 9.11 times 10 to the negative 31 kilograms. And then times 2.9 times 10 to the 7. And then don't forget to square it, right? Because it was mv squared, right? Right there. I swear that's like half of the mistakes that kids make, is always just forgetting to square the velocity at the end there. Okay. So I know that looks like a mess, right? Like it gets a little confusing, but we just gotta get a little bit more used to this. If you want to make sure that you don't make any mistakes going through this, if you want to break it into pieces when you put it in your calculator, it's fine to like figure out the top, right? Like multiply the top together. And then here's a good chunk, right? This is all just multiplying and dividing. So you could put that into your calculator, get that number, and then put all of this into your calculator, get that number, and you could subtract these, right? Because if you try to put this whole thing into your calculator, like, just like this, you might run into some errors there. Like it'll be fine if you put your brackets in the right places, so your order of operations are right. But it might be good just to do them piece by piece, right? So I'd say there's like 3 good pieces there that I put in. So do the top, do this one, and then really you'd want to make sure you subtract these ones on the bottom, right, before you divide it there, because it's like it's in brackets all on the bottom, right? So yeah. So try that out. If you guys don't get the right answer, if you don't end up getting 2.08 times 10 to the negative 11, then we'll try it again, or let's work on that, right? Come into my open hours and we'll figure out how to get there. Okay. All right. So there's my wavelength. We're not even done. we got one more little piece to do here. So that's the wavelength, right? So we just found the wavelength of our scattered photon or X-ray, whatever. Now we need the angle, right? So Compton has an equation for this. So you guys have an equation for this. Our equation is wavelength final minus wavelength initial is equal to h over mc times 1 minus cosine theta. Okay, now we're looking for this, right? We're looking for the angle. So we got to unpack this. All right, so what I'm going to do, I'm going to get the M and the C over to the other side and the H at the same time, right? So there, this will turn into just multiplying both sides by MC. So it's going to be mass times the speed of light times this stuff, right? Wavelength final minus wavelength initial. And then the H would come down too, right? So I can divide by H at the same time there. And that's equal to 1 minus cosine theta. So we're close here. So now all I'm going to do is I'm going to bring the cosine theta over to the left, right? So making it positive, and then bring this whole chunk over to the right and make it negative, right? So I'm bringing this one to the left and I'm bringing this whole chunk to the right. Okay, so that'll be cosine theta is equal to the 1 still over there. So it's going to be 1 and then minus all of that. So minus MC over H times wavelength final minus wavelength initial. Okay. So then you can put this all into your calculator. Really, we're good to go. But when we put this all in, we're going to get like a number like, 0.3 something, right? That's not going to be right. We got to go second cos to get the actual angle out of this, right? So we've got to go, the angle is equal to cosine -1, right? The inverse of cos, and then of all of that. So I'm going to put the numbers in on this step because I don't feel like writing it again. So I'm going to say 1 minus, now the mass, this mass is the mass of the electron. So this is 9.11 times 10 to the negative 31 kilograms. Here, and again, I'm going to put square brackets here to keep this separate. Times the speed of light, which is 3 times 10 to the 8 meters per second. And that is over Planck's constant, so 6.63 times 10 to the negative 34 joules times seconds. And then it's that times, here, you know what? So I'm going to change that. That times my final wavelength minus my initial wavelength. So that's going to be, so our final wavelength there was 2.08 times 10 times 10 to the power of negative 11 meters, right? That was what we just found up here, right? That was our final wavelength. Minus our original wavelength that was in the question was 2.00 times 10 to the negative 11 meters. And phew, that's it. Now you got to put it all in. So if you put it all in, the way I'd probably recommend doing this to avoid mistakes, I would probably put that in first, right? To subtract those guys to figure out what that number would be. And then you can multiply that by this chunk, right? So I can go that times, doesn't matter the order, 3 times 10 to the 8 times 9.1 yada yada, and then divided by 6.63. And then so I'd figure out what that was, and then I'd go 1 minus that number. And then I'd go cos negative 1 of that. Okay, so if you do that properly, so try it out, you're going to end up getting an angle of 48 degrees. Okay, so sorry for the length of this video, but yeah, there's a lot of writing in these ones.